So here's our first integral with trig substitution, and we already discussed that all of your other methods fail, and I want to be very clear that you always try a basic integral first, and this is clearly not basic. Then you think about a u substitution. Could you do that to get things to work? Always try that next. And then you try some of your fancier methods, maybe an integration by parts. We'll talk about another method after this section as well. But it depends on what you see. So because I see a radical and u substitution doesn't work, and I also notice the structure inside that radical seems to lay out really nicely, that I can sort of look at this as a number squared minus a variable squared, then I'm going to go with trig substitution. So I'm actually going to lay that down, okay? Meaning I'm going to say that, well, a must be 1 because 1 squared would give you 1. I'm also going to say that in here, what squared would give me 9x squared? Well, that would be 3x. So I'm going to let u equal 3x. So it kind of feels like I'm doing an inverse trig or something, or a u substitution. I'm not. I'm going to bring it together here. I'm going to pull this and say I'm doing a trig substitution. I'm going to let u equal a sine theta, because that's the structure that I have. I have a squared minus u squared. And so back to our little cheat sheet over here, a squared minus u squared is telling me to make that substitution. I'm supposed to let u equal a times the sine of theta and see where that takes me. So I'm going to do that. Now, anytime you've made a decision like that, let's go ahead and put it in, meaning u is 3x, so let me drop that in, 3x. A is 1, so I guess I'll write 1 times sine x. That's going to be my swap. In my integral, whenever I see a 3x, I'm going to replace it with sine theta. But I want to be really, really clear right here at this moment, you do have a follow-through here of a dx. So I'm going to do this right now. I'm going to take the derivative of the left. The derivative of 3x is just 3. There's my dx. The derivative of sine is cosine. Here's my d theta. And I want to be mindful of the fact that, look, I am switching this integral from x's to thetas, right? So that means I need to get rid of that dx over there. So let's just continue on. If I want this to say dx equals, well, that would be cosine theta divided by 3. I'm going to need that, okay? But I am actually changing this integral. Instead of having the integral of the square root of 1 minus 9x squared, I'm not going to have that anymore. Let's think about what I actually did. I said that 1 was 1 quantity squared, and I said that 9x squared was 3x quantity squared. That totally makes sense. That's how I kind of saw what was underneath there. Now what I'm going to do is do the swap that I was instructed to do. In place of 3x, I'm replacing it with sine theta. So it would be weird for me to carry that dx down. That can't be. I need to get rid of that dx. That has to go away. So I'm going to replace it with what I can legally replace it with, which happens to be, that should be an equal, so which should be cosine theta divided by 3 times d theta. So here comes that follow through. So now this is legal. You have successfully transformed this integral that started out with x's with a dx, and it now is all in terms of thetas and a d theta. So this is good in the sense that you've gotten everything transformed. You can't have any random extra variables of x flying around, although you can have coefficients, right? Because I have that 3 down there, that 1/3. That's okay. I'm going to leave it there for right now. So what I'm going to do is rework this, and let's just play around with that radical. I'm just going to write it like this. Sine theta quantity squared, just sine squared theta. And the reason we made that substitution is because you have an amazing Pythagorean identity that you can use here. I do not have to leave that radical as 1 minus sine squared. What I can do correctly is I can just say, oh, 1 minus sine squared, that's cosine squared. That's a legal swap from all your trig identities if you look at that formula sheet. And what we talked about just in the last section, right, with all of our trig integrals. So that's why they told you to use that trig substitution. The reason is you can use that Pythagorean identity, make this great swap, and yes, the square root of cosine squared, it sure is the cosine. Now, I keep carrying through this cosine divided by 3 because I just don't know what to do with that yet. But let's regroup and look at what I actually have. My integral has now become this. So I have to think from the last section, how do I handle this integral? You've just done a ton of work, and now I'm going to try to evaluate this integral. So when you have a sine or a cosine squared standing alone, there's nothing else here, this is where you have to use that power reducing identity. So I'm just going to write that down real quick. I need the power reducing. Okay. So the power reducing identity, remember, is in place of cosine squared, I can replace it with this. That's a legal swap from your formula sheet. It's an identity, which means it's always true. I'm going to make that swap here because it makes my math work a lot easier. What I'm going to do is actually, I'm going to pull that 2 out, as a coefficient, like a 1/2. So that's going to make this coefficient on the outside a 1/6. And the reason we use that power reducing, just to remind you again, is because it allows me to break up into 2 pieces that cosine squared. I can integrate each one of these separately now. So I can integrate 1 and I can integrate cosine 2 theta, right? So let me kind of play around here. Let me just kind of give myself a little bit of room. The integral of 1 d theta is just theta. I know that feels weird, but the integral of 1 dx is x. So the integral of 1 d theta is theta. What I need here is I actually need to fly back and go back to a u substitution. This is doable. I'm just going to let u equal 2 theta, du equals 2 d theta. And what I end up having here is, well, let's see, I have the integral of cosine of u times du over 2. So that means I have the integral of 1/2 sine of u. I'm sorry, I'm jumped ahead there. The integral of 1/2 cosine of u, which the integral of cosine is sine. So I'm going to throw that in here. So that means my integral down here, my antiderivative, right, is 1/2 sine of u. Well, that's 2 theta. And then outside this whole thing is I have that constant of integration, right? I just had to do this little detour of a u substitution. Some of you might be able to do that in your head, and that's fine. Okay, so the integral of 1 there is theta, and the integral of cosine 2 theta, this big detour you have over here, gives me that term. Now, I wish I could say that we're done, but you have to take a look at what we started with, which was an integral in terms of x. And I did successfully integrate this trig substitution problem, but my answer is in terms of theta, which really doesn't make a whole lot of sense here. So let's take a minute and think about this. I'm going to need to use another identity here. This is why you get a formula sheet, right? You just need to know where to look to find these. On your formula sheet, you have a replacement, a legal swap for sine 2 theta. So I want you to find that. It's in your double angle title, okay? And so sine 2 theta is the same thing as 2 times the sine of theta and the cosine of theta. I'm making that swap for a particular reason. Now again, I didn't address the fact that there was a 1/2 here. Okay, so I want to make sure that is in play. Okay. And then I have the plus c, and I have the theta. Okay. Oops, that should be a 6. Okay. All right, so at least I can cancel out these 2's. So here is my answer at this stage of the game, which doesn't look much better, right? Because I still have my answer in terms of theta and not x. So I need to figure this out. So back in Unit 1, we talked about this. I'm going to highlight something here. I'm going to go right from here, and I'm going to write what this means. I'm just going to rewrite it. 3x equals the sine of theta. I'm going to make this into a fraction because sine is usually, you know, opposite over hypotenuse. I'm going to draw a triangle for theta in such a way, that the sine actually is 3x over 1. So that would be opposite is 3x, hypotenuse is 1. And if you solve for that missing side, remember, right, if I take hypotenuse squared equals leg squared plus, I guess I'm looking for the adjacent side squared, then you end up with the square root of 1 minus x squared. You can kind of see how, like, oh, I know that, I recognize that. That was part of the integral that I was working on. This picture is incredibly helpful because this is a way to represent thetas in terms of x's, right? So let's go back to our answer to this integral, right? Part of my my answer is sine of theta times cosine of theta. This picture right here is going to be your vehicle to recreate sine of theta and cosine of theta in terms of x. So I will do that, okay? So the sine is 3x over 1. The cosine is adjacent over hypotenuse, so that would be the square root of 1 minus 9x squared over 1. I don't have to put that part. Okay. And then let's take a look at what else I got going on. How do I get this theta in here? Well, let's go back up here. Pay attention there. If 3x equals sine theta, let's just come at this and say, then arc sine of 3x equals theta. Just algebraically, you know, let's show that a different way. I don't want to lose anybody. If 3x equals sine of theta, just sort of come out here with the inverse operation. Let's do the arc sine on both sides. So you're going to say, I'm going to take the arc sine of 3x, I'm going to take the arc sine of the sine of theta. These guys cancel each other out just to giving you theta. So theta equals arc sine of 3x. So I'm going to put that right here, arc sine 3x. And of course I have my constant of integration. So you actually are at the final statement here. What I think I'll do is I'll just multiply. I don't want to forget that that 1/6 is going through everybody, and I should probably try to have better handwriting. So first part of my antiderivative here, my integral is 1/6 arc sine 3x. Then I'm going to move that 1/6 through here, so that would be x over 2 times the square root of 1 minus 9x squared plus c. That is certainly a long problem, and you can kind of see the variety of strategies that we used here. Overall, this is a trig substitution, meaning I started this problem with an integral in terms of x, I switched it to a trig function, and then I was dealing with evaluating that trig function. I needed to use some identities along the way, a couple of identities. I used a Pythagorean identity, I used a power-reducing identity, and I used a double angle identity. So there's lots of identities going on. At the end of the day, you have to give an answer in terms of the variable that you were presented with. So there is my answer to this. Okay, so let's take a look at problem number 6, because it's going to be a similar substitution. However, the integral part is a little prettier. So, okay, here's problem 6. What I mean it's the same setup here is, again, we already talked about the fact that U substitution fails. This is not a basic integral. Integration by parts does not seem awesome here. So because I see a radical, that's going to trigger something in my brain, like maybe I'll have to use the trig substitution. Let me play around and see what's in that radical, what is on the inside, and I do see a number minus a function of x squared. So because I see that, that means trig substitution is a viable option, because the point of trig substitution is to eliminate the radical. So I'm going to look at this, and it's the same kind of swap, meaning I have a number minus a function of x squared. So I'm going to make the relationship here. I'm going to say, well, I'm going to let a equal 3, and I'm going to let u equal x. Now again, I'm putting these together, and I'm coming at this with a trig substitution. What that means, just like last time, u equals a times the sine of theta. Now in this problem, u equals x, a equals 3, and that is my swap. Before I actually make the swap, however, I do want to be really clear that there is a follow-through, right, that I'm going to need. I just do it right here. If x equals 3 sine theta, then dx, the derivative of x, I'm going to take the derivative here, equals 3 cosine theta d theta. I do that right away so that I don't forget. That is the number one thing that students will forget. They will forget to replace the dx. Okay, so let's come over here and actually transform this integral using a trig substitution. So anywhere I have an x, I'm going to replace 3 sine theta. Well, right there I have an x squared, so I'm going to write 3 sine theta squared. In the denominator you have a square root, and you have 9 minus x squared. Now remember, x is 3 sine theta squared. Again, in place of dx that has to go, I'm going to replace it with its equivalent, which is 3 cosine theta d theta. So it looks like you made this problem a whole lot worse, but you have to really get in here and kind of simplify the trig. Okay, so let's use our good algebra skills and trig skills. When you're squaring a monomial like this, you have to square the number and the trig function. Make sure that I do that. Same thing under this radical, right? I'm going to square the number and the trig function. And I think I'm just going to put the 3 cosine up here in the numerator. I don't like it when it's off to the side. I feel like I'm going to forget about it. I'm going to do that. And we're going to keep playing around with this. We're going to keep trying to tighten this up and use our trig identities to make this work for us. So I'm going to keep working. And the whole point here is to eliminate that radical. So underneath that radical, I am going to, see how they both have a 9? There's 2 terms and there's a 9. I'm going to factor out the 9, but it's still inside the radical. And then I want you to pay attention to that, because the whole reason that we used 3 sine theta for x is because this is always going to be amazing. 1 minus sine squared, that's that Pythagorean identity, that can be replaced with cosine squared. That's a legal swap. And when I look at that radical, I hope you see you have pretty much successfully eliminated that, because the square root of 9 cosine squared is just 3 cosine. So I can totally cancel out the 3 cosine from the numerator with the 3 cosine from the denominator. And some of you may have recognized you could have canceled out the 3 and the 9 here. It's up to you. Okay. But anyway, here's where we're at. Let me regroup and let's sort of pull all this together. What do I have? I have, well, 1 over 9 sine squared theta. That's 1/9 times the integral of cosecant squared theta. And that's another identity, right? That's a reciprocal identity. The reason I want to go with that is I don't know what the integral of 1 over sine squared is. But when I represent 1 over sine squared as cosecant squared, this is actually a basic integral that you guys need to know. The integral of cosecant squared is negative cotangent. And of course, there's that 1/9. This is not anything that should be a stretch. This is something that you learned back in Calc 1, in terms of all of your integral rules. So you're kind of at the finish line in a way, right? My integral is negative 1/9 cotangent theta plus c, but that's really weird. I can't leave this as my answer because my integral was in terms of x. So I have to do this kind of maneuvering here. Now let's pay attention. What was our substitution? Our substitution was that x equals 3 sine theta. Let me rework that. That means x over 3 equals sine theta. Let me draw that theta. I'm going to draw a triangle with theta in it so that the sine ratio really is x over 3. And when you solve for that third side, right, just using the Pythagorean theorem and kind of working it out, let's see, hypotenuse squared equals leg squared plus adjacent squared, you end up with kind of that thing that you were replacing, the square root of 9 minus x squared. This picture is going to help us switch everything over. So all I have to do is use that picture and represent what the cotangent of theta is in terms of x. So this is why we did this a little bit back in Unit 1 when we were talking about inverse trig. So I saw that negative 1/9. The cotangent, remember, is adjacent over opposite. So the adjacent side is the square root of 9 minus x squared. The opposite side is x. I'm going to put that constant of integration in, and that looks good. I mean, you could box it up from there. I'm just going to kind of make it look a little prettier. Kind of. Okay, both of these are good. Okay, so it doesn't always have to be like a mega horrible problem like problem number 5 that had so many identities, so many switches, so many issues in switching over. This one ended up being a trig substitution that ended up being a basic trig integral, and that's why I need to make sure that you remember everything from Calc 1 and all this fancy stuff from Calc 2. So this is certainly a new method. So we have U substitution that we use most of the time. When that doesn't work, you could try integration by parts, because that's an advanced technique. If that doesn't work and you happen to see a radical of the right layout, then you could try a trig substitution. So in the next video, we'll do the last couple problems.